All right, so let's talk about some properties of functions. So we're gonna cover 6.2 now, and 6.2, like I said, it's really we're just going to be talking about several different properties of functions that are useful for us to know in order to be able to describe, what's going on with functions and things like that. So, one piece of notation that I'll use a lot is if I want to talk about the domain of a function f of x, then I'll just call it dom f, or domain of f. And similarly, I might sometimes say, if I'm looking for the range of a function, I might say range f, right? To describe the range of a function. So I don't have to write out domain of the function, right? I can just say dom of f, right? Okay. So let's say that f is a function, and let's say that some interval ab is a subset of the domain of f. Okay? F is increasing on that subset of the domain if f of x1 is less than f of x2 for all x1 and x2 in the interval ab, with x1 less than x2. It's increasing if the opposite happens, right? If f of x1 is greater than f of x2 for all x1 less than x2 in the interval. And it's constant on AB if f of x1 equals f of x2 for all x1 less than x2 in the interval from A to B. This is all maybe a little bit confusing. This is a confusing way to say the following. It's like if you're looking at a function, and by the way, this passes the vertical line test, so this is a function. It's a weird function. It's probably some piecewise defined function of some kind, but it's definitely a function. Now, if you imagine riding this function like a roller coaster, left to right, then if you're climbing, then the graph is increasing. If you're falling, then the graph is decreasing. And if you're just moving along horizontally, then the graph is constant, right? So for this function, let's find the intervals over which the function is increasing, decreasing, and constant. So where are we increasing, right? In other words, if we read this thing from left to right, where are we climbing? So we're climbing from, it looks like from negative infinity all the way up to negative 3. We're climbing. At negative 3 itself, we start to drop, I guess. So I'm not including the negative 3 in the portion of the graph where we're increasing. But where else do we increase? So we decrease here, then we're constant, then we decrease some more, and then we start to increase again. So from 1 to infinity, I think we're increasing still. Okay? Where are we decreasing? We're decreasing from negative 3 to negative 2, and then we're constant for a while, and then we decrease again from 0 to 1. So negative 3 to negative 2, union 0 to 1. So it looks like we're decreasing on those two intervals. And then where are we constant? We're constant between negative 2 and 0. And then that's it, right? That's the only place that we're constant. One thing that trips students up on this when I'm asking, where it's increasing, where it's decreasing, is that sometimes they mix up the x coordinates with the y coordinates, right? Like, so they might say, oh, well, here it looks like we're increasing from negative 2 up to positive 2 because they're thinking about the y coordinates, negative 2 to positive 2. And then we decrease from 2 to 1, and then we decrease from 1 to 0, right? But that's not what's happening, right? I mean, that is what's happening if you're looking at the y coordinates. But when I'm asking you where the function is increasing, decreasing, and constant, I'm asking for what x values is the function increasing, right? So the x values where it's increasing are from negative infinity up to x equals negative 3, right? And then it's decreasing from x equals negative 3 to x equals negative 2. And then it's constant from x equals negative 2 to x equals 0. Then it decreases again here, right? And then it increases. So that's how we're kind of thinking about this. Let's say that you didn't have a picture, though. We could still determine where the function is increasing, decreasing, and constant. So let's do it. Probably the easiest way to do it is to graph the function if we can. So natural log of x. I know that natural log of x looks something like this. It crosses the x-axis at the point 1, 0, right? But that's basically what ln of x looks like. Question is, where is it increasing, decreasing, and constant? Well, to me it looks like it's increasing everywhere. It looks like it's increasing on its entire domain. Right? So it's increasing from 0 to infinity. It's decreasing nowhere. And it's constant nowhere. Okay, let's do part B. Part B is a parabola. It's been shifted left 2, down 3. So it's got to look something like that. I don't care so much about getting a perfect picture, but I know that it looks something like this. So it looks to me like it's decreasing from negative infinity until x equals negative 2, right? And then it's increasing from negative 2 to infinity. So it's increasing from negative 2 to infinity, and it's decreasing from negative infinity to negative 2. It's constant nowhere. It's never constant. Okay. Part C, secant function. Let's see what's going on with the secant function between negative 3 pi over 2 and positive 3 pi over 2. Well, at negative 3 pi over 2, it has an asymptote. And then it has another one at pi over 2. Sorry, negative pi over 2. But it does have another one at positive pi over 2 as well. And then another one at 3 pi over 2. So, and then, so this is 1 and negative 1. It looks like this, right? Right, so this is what the secant function looks like if the domain is restricted between negative 3 pi over 2 and positive 3 pi over 2. So this particular function really does just stop here. It doesn't continue on it doesn't continue on to the left or to the right because our domain was restricted. We're restricting our attention to just looking between negative 3 pi over 2 and positive 3 pi over 2. So where is this thing increasing? Well, it might be useful to label some of these things. This is negative 3 pi over 2. This is negative pi. This is negative pi over 2. Pi over 2, pi, and 3 pi over 2. Okay, so where is it increasing? It looks like it's increasing from negative 3 pi over 2 to negative pi, and then it starts to decrease, but I'm going to keep track of all the places where it's increasing. So from negative 3 pi over 2 to negative pi. Then it starts to decrease. And then it's still decreasing up here, but then it starts to increase from 0 to pi over 2. Okay? And then it's still increasing from pi over 2 to pi. And then starts to decrease again. Okay, so that's where it's increasing. Where is it decreasing? It's increasing, then it decreases from negative pi to negative pi over 2. Then up here it's decreasing again from negative pi over 2 to 0. Notice that, I'm not including the negative pi over 2 in the place where it's decreasing. That's because at x equals negative pi over 2, it's impossible to determine what's happening, right? Maybe you could say, well, it increases simultaneously, or it instantaneously increases from negative infinity to positive infinity. But no, we can't really say what's happening at negative pi over 2. But it's decreasing, decreasing, increasing, increasing, and then decreasing again from pi to 3 pi over 2. From pi to 3 pi over 2. So there you go. And it's constant nowhere. So it's never constant. Good thing I didn't give us some crazy absolute value function. Those things can be constant at certain places though, right? It would have been a good example to look at, but a lot of work to graph. So there's that. All right. So increasing, decreasing, constant. A notion that's related to the notion of being increasing, decreasing, or constant is the idea of relative extrema. Okay, so a relative maximum of a function is a point where the function value is larger than any other function value within a certain interval, right? A relative minimum is a point where the function value is smaller than any other function value in a certain neighborhood, I guess. And then a relative maximum or minimum is called a relative extremum. In calculus, you're going to talk about relative extrema a lot. It's going to be a big topic for good reason, right? Relative extrema are important when it comes to applications and when it comes to graphing curves and things like that. But this particular definition that I'm giving you here is a little bit, it's not very precise, okay? But it's good enough for our class. It's good enough to give us an intuitive understanding of what relative extrema are. So I'm going to leave the precise definition to your calculus instructor. And then one thing to note about relative extrema is that they don't have to be absolute extrema. So a relative minimum is not necessarily the lowest point on the graph. However, it is the lowest point in some portion of the graph. Okay, and we could say something similar for a relative maximum. So let's look at a couple examples. So for this first example here, let's find all of the relative extrema of this function. So the relative extrema. Well, here I'm going to have a relative maximum. It's not the absolute maximum, right? Because from this point on, this line is just going to continue on and on forever. So this function doesn't have an absolute maximum, okay? But it does have a relative maximum there, and it has a relative maximum there. So the relative maxima are, they take place at the point -3, 2, and 2, 1. Okay, relative minima. Well, notice that we don't have an absolute minimum because this is going to go on and on forever in the negative direction. So it's not going to have a smallest value overall, but it does have some relative small values like this one and this one. Those are both relative minima. So the relative minima would be the points -1, -2, and 5, -2. Okay, so that's how relative extrema work. Now, one thing that you might note is that the relative extrema occur at places where the graph changes direction from increasing to decreasing or from decreasing to increasing. That sort of begs the question, well, what happens if the function is constant, right? And that's why I was saying earlier that this definition is not very precise because it doesn't help you to determine what to do when you have cases where you have a bit of the graph that's constant. Like, would those be considered relative minima, relative maxima? What about the values in between? So I'll leave that to your calculus instructor to hash out all the details there. But let's do some more. So where we're not given the graph and we have to come up with the graph ourselves. I think all of these are the same functions as they were from the previous page, but this time we want to find the relative extrema. So for natural log of x, remember natural log of x looks something like that. This function doesn't have any relative extrema. It doesn't have a relative maximum. It doesn't have a relative minimum. So no relative extremum or extrema, right? Extrema is the plural of extremum, right? So no relative extrema. What about part B? This one was a parabola. It's a parabola with vertex -2, -3. So it looks something like this. So this point right here, the vertex, is a relative minima. Actually, it's the absolute minimum of this graph. This graph never gets below that. So it's an absolute minimum. But it's also a relative minimum. So we can say our relative minimum is the point -2, -3. Relative maximum, there is none. Okay, and then we have our old friend, the secant function. Let's sketch this quickly. So an asymptote, 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 and we said it went like this, and like this, and like this. And by the way, this is -1, this is +1. Okay, so these two values right here are going to be, this is kind of trippy, but these are going to be relative maxima, right? Because within this neighborhood, right, if I just clip this neighborhood, this is the biggest value in that neighborhood. And this is the biggest value in this neighborhood. This value right here is a relative minimum. So the reason I say it's kind of trippy is because our relative minimum is larger than our relative maximum, which is kind of a weird thing, right? But given the definition, right, within this neighborhood, this is the largest value, so it's a relative maximum. Same thing over here. Within this neighborhood, this is the smallest value, so it's a relative minimum. Okay? So our relative minima are, or we only have one relative minimum, right? It's this point right here, the point 0, 1. Our relative maxima, this one we do have two of. We have a relative maximum here at, this is -pi, so at -pi, -1, and then another one over here at +pi, -1. Okay. So there you go. Relative minima and maxima, or in other words, relative extrema, right? That's how those things work. This is going to be a big topic in calculus. Another property of functions that can be pretty useful is the concept of even and odd functions. The reason this concept is useful is because it tells us about symmetry. So it's very useful when we go to graph a function. But here's how even and odd works. So a function f is even if f of -x equals f of x for all x in the domain. F is odd if f of -x equals -f of x for all x in the domain. So let's talk about this symmetry, and then I'll give you some examples of this, right? But if you have an even function, then that means the graph is going to be symmetric with respect to the y-axis. So in other words, if you fold the graph along the y-axis, and the two halves of the graph meet up, then you've got symmetry about the y-axis. That means that your function is an even function. Odd functions are symmetric about the origin. That means if you fold the graph along the y-axis, and then fold it again across the x-axis, right, then the two halves of the graph will match up. So if that happens, then you've got symmetry about the origin. You may recall that we have even and odd identities for the trig functions, right? Some of the trig functions are even, some of them are odd, right? In fact, there are two even trig functions, secant and cosine, are both even functions, and the other four trig functions are odd, right? Sine, tangent, cotangent, cosecant, they're all odd functions, right? And so consequently, right, so the even odd identities for like sine was this, right, because sine is an odd function, whereas for cosine it was this because cosine is an even function, right? Well, let me pull that down, sorry. So sine is an odd function, so this was the identity for, this was the even odd identity for sine, and cosine is an even function, so this is the even odd identity for cosine, right? So it matches with what we're saying here about even and odd functions. Let me just show you how you would determine if something is even or odd. So we'll determine if it's even, odd, or neither, because it's possible that it's neither even nor odd, right? So we'll determine that algebraically, and then we'll take a look at a graph, okay, to see if it kind of coincides. Excuse me, to see if it coincides with what we determined algebraically. So to determine if you have an even, odd, or neither, then what you're going to do is plug in f of -x, right? If I plug in f of negative x, I get 3 times negative x to the fourth minus 5 times negative x squared. And then you simplify this thing. And when you simplify it, if you just get the original function back, then that means that f is even. On the other hand, if you simplify it and you get the negative version of the function back, then f is odd. So what do we have in this case? We have, well, negative x to the fourth. You can distribute exponents across multiplication. I'm thinking of this as a negative 1 times x. So if I distribute the negative 4, I'm going to have negative 1 to the fourth power. Now, negative 1 to the fourth power is just positive 1, right? So saying negative x to the fourth power is the same thing as saying positive x to the fourth power. This is just 3x to the fourth power. And the same thing here, right? Negative x squared is just the same thing as positive x squared. So this is going to be minus 5x squared. And if you look at that, that's the same thing as the function we started with. That's just f of x. So f of negative x equals f of x. That means that f is even. Okay? And graphically, I mean, we could graph this by hand. This is just a polynomial function, right? This is x squared times 3x squared minus 5. So you're going to have a 0 at 0, multiplicity 2, and then you're going to have another 0 at plus or minus square root of 5/3. But that's definitely going to be symmetric, right? It's like, so you have a 0 here at 0, then you have another 0 here at square root of 5/3, and you have another 0 over here at negative square root of 5/3. These two have multiplicity 1, so the graph crosses through. Here it just touches, right? The end behavior is the same as 3x to the fourth, so it's going to go up like this. So it's going to look like this, right? Looks kind of like a W. So you can tell that has the symmetry that we were talking about, symmetry about the y-axis. If you take this graph and you fold it across the y-axis, this half of the graph is going to meet up with this half of the graph, right? They're gonna match. So definitely, right? F is even. Let's look at part B. Part B, we have 4x to the fifth plus 2x cubed. So again, if I want to determine if this is even or odd, or possibly neither, I would plug in f of negative x. In this case, I would get 4 times negative x to the fifth power plus 2 times negative x to the third power. Now, negative 1 to the fifth power is negative 1, right? So this is the same thing as saying 4 times negative 1 times x to the fifth. And this is the same thing as saying 2 times, right, negative 1 cubed is still negative 1, so this is 2 times negative 1 times x to the third. In other words, that's negative 4x to the fifth minus 2x cubed. Now, if I factor out a negative, then I get 4x to the fifth plus 2x cubed. And 4x to the fifth plus 2x cubed is just f of x, so this is negative f of x. Okay, so that's interesting, right? So note that on this example, f of negative x was equal to negative f of x. Well, so that means f is odd. Okay? Now, what does the graph of this thing look like? We can factor out a 2x cubed, and we would be left with 2x squared plus 1. Oh, that's really strange. Because here you're not going to get any real zeros, right? So your only real zero is at 0, and it's a multiplicity 3. So it's going to pass through the x-axis right there. But I'm sure that there's some more interesting stuff going on. In order to get a good looking picture, I might have to go to Desmos for this. Let's do 4x to the fifth plus 2x cubed. There you go. Oh, no, it's not very interesting. It just looks like a normal cubic function. But notice that it has symmetry about the origin. Right? It has symmetry about the origin. Right? So the function looked kind of like this. But it has symmetry about the origin. If I fold this in half across the y-axis, then it's going to look... then the top half of the graph kind of looks like this now. And if I fold that again across the x-axis, well, then it's going to match up with this piece. So you've definitely got that symmetry about the origin. Okay? So yeah, f is odd. Okay, let's look at part C. So to determine if this is even, odd, or neither, I'm going to plug in negative x. Hopefully by now you've caught on to the fact that if you have an even exponent, this is just the same thing as positive x to the fourth. And if you have a negative exponent, then that just changes the sign. So what you get is x to the fourth minus x cubed. Now, that's not equal to f of x, right? That's not equal to f of x. So definitely this is not an even function. If we take out a negative, then we would get negative x to the fourth plus x cubed. But that's not f of x either, right? So this is not equal to negative f of x either. So it's not. So f of negative x is not f of x, and it's not negative f of x. So this is neither. It's neither even nor odd. Okay. I'm not going to look at the graph, but the graph is not going to have any symmetry. Maybe I will. Maybe I will, just to show you that there's no symmetry here. Right? We've got x to the fourth plus x cubed. Yeah, so no symmetry, right? Definitely the left-hand side is not going to match up with the right-hand side. And anyway, so no symmetry, right? Another thing that I'll point out about these three examples, right? Notice that when you're dealing with polynomials, it's pretty easy to tell if f is even or odd. It's going to be even if all of your exponents are even. It's going to be odd if all of your exponents are odd. Okay, that's probably where the names come from. I don't know for sure, but I would imagine that's where the names even, odd come from. If you have a mixture of even and odd exponents, then the function is not going to be even, is going to be neither even nor odd. But this idea about even and odd functions, it extends to things that are not polynomials, like the trig functions, right? They still have even, odd properties. And exponentials, right? You could do the same thing. You could say, well, what is f of negative x? Is this an even function, an odd function, or neither? F of negative x would be e to the negative x. If you like, you could call that 1 over e to the positive x. But it's pretty clear that this is not the same thing as f of x. And it's also not the same thing. It's also not the same thing as negative f of x, right? So this is something else entirely. So this is neither. This is neither even nor odd. We can graph e to the x. We know that e to the x looks something like this, right? So yeah, it's not symmetric across the y-axis, and it's not symmetric across the origin. If I fold and then fold, the pieces don't match, right? So this is neither. Okay, one last property of functions that I want to talk about is the one-to-one property, or injectivity. There's another property of functions that goes along with it called surjectivity, or onto, right? We're not going to talk about that in this class, I don't think. At least we're not going to talk about it in this section. I know that for sure. But what we do want to talk about is the one-to-one property, or an injectiveness. Injectivity is the word, not injectiveness. Injectivity. Anyway, so a function f is injective or one-to-one, right? Those two terms mean the same thing. They're interchangeable. So f is injective or one-to-one if x1 not equal to x2 implies that f of x1 does not equal f of x2 for all x1 and x2 in the domain of f. In other words, if you have two different inputs, you better get two different outputs. Otherwise, f is not one-to-one. Okay, to put it another way, in order to be one-to-one, a function cannot map two different inputs to the same output. Okay, so a function sends each input to exactly one output, right? That's just a function in general. A one-to-one function sends each input to exactly one output, and each output only has one input being mapped to it. So let me draw you a picture of this, right? So let's say that this is your domain and this is your range, okay? If you have a function that maps 1 to 2, 2 to 4, and 3 to 6, then this is a one-to-one function, right? This is a one-to-one function, okay? If you have a domain that's, say, 1, 2, 3, and then a range that's, say, 2, 4, and your function maps 1 to 2, maps 2 to 4, and it maps 3 to 4. Each domain element is getting sent to only one range element, so this is a function. But it's not one-to-one, because each range element, or some of the range elements have multiple domain elements attached to them. So this is a function, right? But it's not one-to-one. Okay? And then finally, just to sort of round out the discussion, let's say that your domain is made up of the elements 1 and 2, and the range is made up of the elements 2, 4, and 6. If you had this kind of mapping, this is not even a function, right? Because you have a domain element getting sent to two different places, so that's not even a function. This is a relation. It's a relation, but it's not a function, right? This is a function, but it's not one-to-one. This is a one-to-one function, right? Everything is mapped up one-to-one, okay? Algebraically, to show that a function is one-to-one, we begin by assuming that we have two output values that are the same, and then we show that if that's the case, the input values must also be the same. Now, to show that a function is not one-to-one, the only thing we have to do is provide a counterexample. In other words, we just need to give one example where we have two different outputs that yield this, or sorry, two different inputs that yield the same output. Right? If you can give just one example of that, then you've shown that the function is not one-to-one. So let me give you some examples. Let's determine if these functions are one-to-one, and if they're not, let's provide a counterexample. So to show that this thing is one-to-one, we would start off by assuming that f of a equals f of b. And then what we hope happens is that we hope that we can show that a equals b. So let's see, if f of a equals f of b, that would imply that 2a minus 6 equals 2b minus 6. Right? I'm just plugging in a to f of x and b to f of x. Well, if that's true, then I can add 6 to both sides to get 2a equals 2b. And then I can divide by 2 to get a equals b. Sure enough, right? Therefore, f is one-to-one. Now let's do this for f of x equals x squared, right? So to show that f of x equals x squared is one-to-one, we would start off by assuming that f of a equals f of b. That would imply that a squared equals b squared. And if that's the case, I can take the square root of both sides. But remember, when you take the square root of both sides of an equation, you have to have a plus or minus, right? So I know that a equals plus or minus b. Okay, so that's interesting, right? So I cannot conclude that a is the same thing as b. They might not be the same thing. They might be negative. B might be the negative version of A, I guess you might say, right? They might be opposites. That's the word I was looking for. A and B might be opposites, right? So my guess is that f is actually not 1 to 1. Actually, it's not a guess. I know that f is not 1 to 1. To show it, I just need to give a counterexample. So I can say something like this. What would be a good counterexample? Well, this gives us a hint, right? It tells us that, well, if a and b are opposites, they're going to give you the same output. So like if x is 3, you're going to get the same output as you would get if x is negative 3, right? So we could say, for example, f of 3 equals f of negative 3, right? They both equal 9, right? 3 squared equals negative 3 squared, right? 9 equals 9. So f of 3 equals f of negative 3, even though 3 does not equal negative 3. In other words, you have one output value that has two different output values that map to it, and therefore f is not 1 to 1, right? Therefore f is not 1 to 1. Okay, so that's how you can tell if a function is 1 to 1 algebraically. Graphically, it's even easier to tell if a function is 1 to 1. And to show you to show you how this looks graphically, let's just practice. Let's see, is f of x equal absolute value of x 1 to 1? Well, let's see. Here's what f of x looks like. Is it 1 to 1? Right, so this is f of x equals absolute value of x. Is it 1 to 1? Well, in order for it to be 1 to 1, we would need to have only one input value for each output value. But notice, this output value right here, one of the input values that maps to it is that value, but there's another one, right? Okay, so you have two input values for one output. So f is not 1 to 1. Okay? What about g of x equals x cubed? G of x equals x cubed looks something like this, right? Is it 1 to 1? Well, for each output value, you're only allowed to have one input value. So if I choose this output value, right, whatever this output value is, there's only one input value attached to it. If I choose this output value, again, only one input value attached to it. So yeah, G is 1 to 1. To make this even easier, what we can say is this. Notice that here, if I pass a horizontal line through this function, I'm hitting two places at once. Whereas here, I can draw any horizontal line I want, and I'm never going to hit more than one point at a time. So what that tells us is that 1-to-1 functions pass the horizontal line test. Okay, so all functions pass the vertical line test, but only 1-to-1 functions pass the horizontal line test, right? So we can use the horizontal line test to determine if a function is 1-to-1. For example, if we have the function f of x equals 3x plus 2, well, that's just a linear function. That's just a straight line, right? It has a y-intercept of 2 and then a slope of 3, so it looks something like that maybe. That's clearly 1-to-1, right? It's going to pass the horizontal line test easily, right? So this is 1-to-1 for sure. What about tangent x? Well, tangent x has some asymptotes at a bunch of places, and then it looks like this, right? So is tangent x 1-to-1? The answer is no, right? You draw a horizontal line, you're going to hit in infinitely many spots, right? So this is not 1-to-1. It's very badly not 1-to-1. Okay? But what if you restrict the domain of tangent? What if you look at tangent x, but you only restrict your attention so that x is between negative pi over 2 and pi over 2? That's where you have asymptotes, right? Well, so then you get this picture. And it doesn't repeat anywhere because we've restricted our attention. Is this function one-to-one? And the answer is yes, right? Now it's only going to hit in one location. Draw any horizontal line you like, it's only going to hit in one location. So this is one-to-one now. That's an important fact. And that's true about trig functions in general, right? Trig functions, generally speaking, are not one-to-one, but usually you can restrict their domain in such a way that with a restricted domain, you get like an entire copy of the function, but on that restriction, it's still one-to-one. Okay, so that's a really nice thing about trig functions. And I think that's all I have to say about properties of functions for now. So that's it for 6.2. We'll see you in 6.3.